In this video, we present a city-wide model designed to simulate the telecommunications performance of a real 4G cellular infrastructure providing service to IoT devices. We have included real locations for devices expected to be a part of the smart city infrastructure of the island of Montreal. This tool can become a powerful tool to help telecom providers as well as IoT application developers to study the dynamic patterns of interaction. Understanding the interplay between the traffic produced by IoT applications and the background traffic of a city is crucial in ensuring the required quality of service for each of the IoT-enabled services in a smart city. In this video, we demonstrate how does our simulator of LTE machine-to-machine traffic works. While the simulator can be used via command line instructions, in this video we show its web interface. We start by launching the simulator using the launch button. The only option active right now is the large LTE simulation, which we will click right now. The simulator shows the island of Montreal, Canada, and the areas of each of the base stations in the city. They can be shown as either Voronoi or what we call regions. Voronoi are built using the real locations of the base stations. On the other hand, regions show the areas of the city for which a base station is the one with the highest received signal strength. In our simulator, propagation is modeled, and each area of the city has associated an ordered list of the antennas with the highest RSS values. This information is used to define the so-called regions. We will now launch one simulation. To give the simulator the parameters for a new scenario, we press the New Simulation button on the upper border of the interface. We first define the machines that will be creating the traffic in the simulator. We start by using one of our presets, the smart meters. The simulator loads the locations of the residential smart meters, which are located in each of the houses of the island, whose location comes from public databases of the city of Montreal. This preset brings a specific packet size, a packet generation distribution, and its parameters. We now show how we can create a custom-made type of traffic source for a new hypothetical IoT application. We start by clicking on this button to add a new machine and define its name. In our case, we want to simulate a type of machine that generates a very intense traffic. We have created random locations for micro PMUs across the city. Let's choose them to create 50,000 of them. After adding a value for the packet size, we take advantage of the opportunity to show another distribution, the periodic one. Because we want to stress the system in this scenario, we will make each micro PMU generate one packet exactly each 20 seconds, perfectly synchronized with the other micro PMUs. This may increase the chance of collisions happening among the user equipments in the simulation. If the user wants to analyze the results of the simulation along the time axis, it is possible to activate the advanced simulation mode, which will, on one hand, allow the user to visualize graphs of different kinds of indicators across time, and on the other, will allow her to download a CSV file with more information that can be used for further data analysis and machine learning. We can choose the level of precision or granularity of the graphs and the CSV. For this scenario, we will work with 10 minutes aggregations. We can also modify the parameters related to time, such as the simulation duration, which is set by default to 1 hour. In order to make this scenario more interesting, we are going to program the occurrence of failures. To do that, we activate the failures option seen below and enter the interface to parameterize the failures. We can either generate random failures across time and in random locations, or we can define them tailor-made by clicking on the specific failure button. We can choose the level of severity and the recovery time of the failures, as well as when they start and their duration. It is very important not to forget to indicate which areas of the city, in other words, base stations, will experience a failure. We will choose now some areas. As can be seen, we have selected several areas surrounding this region. Machines finding that their base station is not working will access the next antennas in the ordered list of RSS values these machines have. Therefore, we expect many of them to have as a second option the region in the center of the failing area. We may expect the performance in that cell, therefore, to deteriorate. Before launching our simulation, we want to point out that the user can save the simulation parameters as a JSON file, or load previously defined parameters as well, which is important for reproducibility. This simulator is presently running using multi-threading in a server in Compute Canada. For now, let us skip the video until the moment the simulation ends. We can see now how the interface shows the regions as a heat map, where the color varies according to the value of certain indicators, in this case, total traffic. There are other indicators that can be shown, for example, collisions rate, which might be interesting as it is a measure of the performance we expect to be affected in our scenario. We can also click on each area, such as this one that is marked as one presenting a failure, and see some statistics resulting from the simulation, as well as a graph where the horizontal axis is the time, and there are several indicators, whose 10-minute aggregations are plotted against time. Let us see the region where we expected to see some congestion due to the failures. Let us study for now the collision count over time for the application with more intense traffic, the micro PMUs. We can see that at the same time the failure starts, there is a dramatic increase in the number of collisions, confirming our expectation that many machines normally served by other base stations would send their access requests to the base station serving this area, increasing therefore the probability of collision between packets. You are invited to visit our simulator in the URL traffic m2m modeling.com and try your own simulations.